All right, everyone. As you can see, we've got about 5 modules left to look at in calculus. There's 2 optional ones which we haven't got in our timeline, but I'm thinking of what I'll do is I'll record the content for it anyway, but it is explicitly, or it's explicit content for kinematics. So 18F and 18G are applying differentiation to kinematics and applying any differentiation to kinematics. So we're not, it's not going to be accessible, it's not going to be on the exam or on the learning task, but for those of you, especially, once again, doing engineering or physics, you will absolutely be using calculus in the context of kinematics. So you may want to look at that. All right. Today, we're going to look at two different modules. The first one, 18A, we're going to look at tangents and normals. And then I'll give you a bit of time. You can have your independent practice, ask some questions. And then later on today, we will look at rates of change. So, everyone's got the notes. The learning intention for the first module is to explore techniques for determining the equation of the normal and the equation of the tangent lines of a function at a point. So hopefully you've done this kind of technique before, but maybe not in the context of, okay, well, starting off with a cubic or a quadratic, and then at a certain point finding the normal or the tangent. All right, so let's define these 2 things first. Well, if we can find a tangent to the curve or the normal to the curve, the 2 things are going to be perpendicular to each other. So what you see in this is this curve here, y equals x minus 2 squared plus 1. And then this dashed black line is tangent to the curve. And at a right angle here is your normal line, which is the dot here. So in other words, at this point here, 3, 2, and I know that's been cut off on yours, so I've modified it since then. The tangent to the curve at point 3,2 is this one here, and at 90 degrees to that is your normal line to the curve at point 3,2. Now what we can see is these are just linear lines, straight lines, linear functions. They will have a y-intercept. This one will have a y-intercept down here, and this one will have a y-intercept here. They also both have a gradient, and that's where most of our kind of skills come into play. The gradient of a normal multiplied by the gradient of a tangent equals -1. You've used that before, hopefully that part's just revision. You would have defined the formula m1 times m2 equals -1. Cool. So if we can use the derivative to find the gradient of the gradient function, or the tangent line, then we could use this relationship here. So, say we know the gradient of the tangent line from the derivative function at a point, then what we can do is we can use that to find the equation of the gradient of the normal line. And once we know both gradients, we can then go one step further and apply those both to this formula here. Y equals y1, y take away y1 equals m bracket x minus x1. Well, this formula here in Aqua is a method for determining the equation of a straight line given a point and knowing the gradient. So, let me just jot those 2 down on the side that we can refer back to in just a moment. We've got our gradient of the tangent times gradient of the normal is equal to -1. And we've also got that a linear relation given a point and a gradient can be expressed by this, where the point was x1, y1. All right. Example, is there any questions about any of the definitions there? Normal line, tangent line, formula for relating to gradients. Okay. So let me scroll down so we can have all of the space, because we're probably going to need it here. Find the equation of the tangent and the normal, so the full equation, not just the gradient, to the curve y equals x cubed minus 2x squared at point 1, negative 1. All right. So we've been working on this technique called differentiation to get the derivative or the gradient function. So if we, the terminology we're using here is y, so the derivative function we could define as not dy over dx. We use this terminology, dy over dx, because the formula has been given to us in terms of y. You could say where y equals fx and then use that terminology, but let's just use these interchangeably. Well, the derivative function is equal to 3x minus 3x squared minus 4x. Well, to get the gradient of this tangent line at this point, let's substitute in our x value. Sub in x equals 1. And what we get is dy dx equals 3 times 1 squared minus 4 times 1 equals negative 1. So I'm just going to pause here. Can anyone tell me what is this?
The gradient of the tangent at that point.
Yes, what we've found is the gradient of tangent line at x equals 1. So in other words, for this formula, we've found that m is negative 1. Can we use that? Yes, we can. So I'll just change colour to, yep.
Thanks, Michaela.
Yep.
Just got next interview.
Is it running a bit early, is it?
Thank you.
Yep, that's all right.
Sorry, we're running a little bit early.
That's all right. All right. Well, now let's plug this information. We've now got our gradient of our tangent line. We know the x, y that we want to use. So let's substitute that into here to get our equation of the tangent line. Y minus negative 1 equals the gradient, negative 1, times x minus 1. Y equals negative x. Okay. So we now have a relation here between x and y. Or we have an equation of the tangent. Because that's actually one of the things we've been asked for, the equation of the tangent. Now, let's refer now to this formula here. M1 times M2 equals negative 1. Or two perpendicular lines. The gradient of two perpendicular lines multiplied together is negative 1. Well, we then can say that, the gradient of the normal, which we don't know yet, is going to be equal to negative 1 divided by the gradient of the tangent, which we do know, or negative 1 again. So the gradient of the normal line in this case is going to be positive 1. So then if we, once again, use that same point, but the second gradient in our formula for obtaining a straight line formula. Yep. Y minus negative 1 equals positive 1 this time. X take away 1. So y equation of the normal. At the point 1, -1. For the curve, y equals x cubed minus 2x squared. So let's just kind of summarize what this technique is. We're given a curve, we're using differentiation to find the gradient function. We then use a point, or specifically we use the x-coordinate of a point to evaluate the gradient of the tangent line at that point. We then use the gradient of the tangent line, substituting it into this formula. With the point, we can obtain the equation of the tangent line. And then going just a little bit further, we can evaluate or determine the equation of the normal line.